going on page 39 when we are done. Right? So we have what are called power functions. Okay? So an example of a power function would be f of x equals a times x to the nth power, where a cannot equal 0, because if a equals 0, the whole thing equals 0, right? And n cannot equal 0, because that would give me as a 0 exponent, and anything to the 0 power is what? 1. Thank you. It is not 0, it is 1. Good job. So that would just mean that this would just be a then, and that wouldn't be a power function because it would just be a constant. All right, so a power function is a type of monomial function, meaning one term. So if I have 3x squared, that's a power function. If I have 3x squared plus 4 or 3x squared plus x, not a power function because it's not a monomial. Mono meaning one, nomial meaning term. Okay, so it's a single term thing. So we're going to draw sketches of the ones that we can do. A lot of our parent functions that we have looked at are monomial functions, but we're only going to look at specific ones here. So my constant would just be f of x equals c. C being a constant, so that's like y equals 3, something like that. And it would just look like this. It's just the horizontal line. Okay. Then we have linear, f of x equals x, and we definitely should know what that one looks like. Quadratic, f of x equals x squared. Definitely know what that one looks like. Cubic, f of x equals x cubed. You should not even hesitate thinking about what these look like and drawing a quick little sketch of them. Okay. So then we have quartic and quintic, which you may have not talked about before, or if you did, you may not remember them. We should at least be able to get the little equations, even if you're not sure what they look like. Quartic would be f of x equals x to the what? 4th. And quintic, f of x equals x to the 5th. Okay, those make sense? Okay, so here's what a quartic parent function looks like. And here's what a quintic parent function looks like. They look like the quadratic and the cubic. Now, I don't have a scale on my x and y axis, so I don't have any anchor points or anything. The anchor points would definitely be different, but the general shape would be exactly the same. And so if we had, so this is x to the 4th, x to the 5th. This is what it would look like for x to the 6th, 7th, 8th, 9th, 10th, 11th, right? Any power function to the 4th power, to an even power is going to look like a quadratic. Any power function to an odd power is going to look like a cubic, okay, every single time. Now, we get past a power function, lots of things go crazy and look different, but that's what happens here, okay? Now, we talked about even and odd functions, but remember, we also looked at even and odd powers, and those are two different things. They can be the same, they can go hand in hand, but not always. So right now, we're not talking about even and odd functions, we're talking about even and odd powers. So if the function has an even power, then it is symmetric about the y-axis, which is also true for an even function. It's not true for every function that has an even power, only when they were power functions, talking about these monomials here. If the function has an odd power, and it's a monomial function or a power function, then it is symmetric about what? The origin. Good. If it's symmetric about the x-axis, then it's not a function. So that's why we're not worried about the x-axis. Okay? Everybody with me? All right, awesome. Okay, so now let's talk about end behavior of our power functions. So if I have an even power positive coefficient, so in this case it's f of x equals x squared is what we have here, but it could be x to the 6th, x to the 128th, it doesn't matter. It's going to basically look like this because I have no scale. And my end behavior means I'm only concerned about the ends, hence the name end behavior. So as x approaches infinity, what does f of x approach? Infinity. And as x approaches negative infinity, f of x approaches infinity. Okay. Even power, negative coefficient. So negative x squared, or negative x to the 8th, or negative x to whatever that's even. All that's happening here then is a reflection in the x-axis. This is my end behavior here. So as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches negative infinity. Okay, we good? Even is either up, up, or down, down. And that's going to become hugely important to us starting tomorrow. Well, today, but tomorrow. Okay, so odd power, positive coefficient. So x to the 3rd, or the 7th, or the 125th, or whatever. This is the ends. It models a cubic. So as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches negative infinity. Odd is opposite, right? Odd power negative coefficient, that means we take our concept of a cubic looking thing and we reflect it in the x-axis. So it changes. And as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches infinity. Okay. Everybody good with that? Okay. So we're going to graph a couple. We're not going to fill in all this information. I just didn't take it off because that took time that I didn't have. Because we're not going to spend a ton of time graphing these. I just want you to kind of see the concept here. So I have f of x equals 3x to the 6th. So my parent function for this is just x to the 6th. And I know that that models a quadratic, right? What is the only transformation that's happening with this? A vertical stretch by 3, right? So when I do my anchor points, I got 0, 0. So I put my pencil on 0, 0. A vertical stretch doesn't do anything to that, so I still have that. My next anchor point is 1, 1. Not because everything is 1, 1, but the reason everything ends up being 1, 1 is because if I take an x of 1 and I substitute it in here, 1 to the 6th is 1. So start at 1, 1, vertical stretch of 3, my y value becomes 3. Then negative 1, 1, because if I substitute a negative 1 in here, I get 1. So that's where I start. Then I do a vertical stretch of 3. If this was a quadratic, my next anchor point would be 2, 4. It's not 2, 4, but it's up there somewhere. It's 2, and then I substitute it in here, and 2 to the 6th is 2, 4, 8, 16, 32. 32 times 2. 64. So it would be my anchor point. The anchor point is 264. So I'd go to 264, which is way off my graph. Then I multiply that 64 times 3, which is even further off my graph. There's no chance of even trying to graph it. So there's really no chance of doing the negative 2 either. But what that does tell me is that when I'm drawing this in, I'm not going to be really close to this side. Like I'm still really close here because it's really skinny up there, right? And then it just looks like this. And the only thing we're going to talk about is the symmetry. What kind of symmetry does it have? Y-axis symmetry. Okay. Everybody with me so far? All right, so let's do an odd one. So here I have f of x equals negative 2x to the 5th. So my parent function is x to the 5th, which is going to model a cubic. My transformations here are a reflection in the x-axis and a vertical stretch by 2, right? My first anchor point, 0, 0. Put my pencil on 0, 0, and nothing changes. Next anchor point is 1, 1. So I put my pencil on 1, 1. I reflect in the x-axis, vertical stretch by 2. What's my next anchor point? Negative 1, what? Negative 1, because negative 1 to the 5th is negative 1. So -1, -1, reflecting the x-axis, vertical stretch by 2. My next anchor point, if this was a cubic, it would be 2, 8, but it's not 2, 8, it's 2 what? 32, because 2, 4, 8, 16, 32. Count on your fingers, that's the way I do it. So I'd be at 2, 32, right? Reflect, and then go way off my graph. So it's not, I can't do anything, but again, that does tell me it's super skinny. So it would look something like this. And what kind of symmetry does this have? Origin. Any questions at all? All right, so that's power functions. Grab your other one. Let's talk polynomial functions. This one is going on page 40 when we are done. Okay? So we have a polynomial function, and we're going to spend some time on polynomials. They're hugely important to us. We get this crazy looking equation to describe polynomial functions. And unfortunately, sometimes to be able to generalize it to work for any polynomial or any whatever it is we're talking about, it looks insane when what we're doing isn't really that hard. It's just telling you that whatever exponent you start with, so let's say that this is x to the 5th, then this would be x to the 4th, x to the 3rd, like all the way down. That's what all that nonsense looks like. And then this a sub n just means this is the coefficient that goes with this one, and so forth and so on. So an example of a polynomial function, f of x is equal to 3x to the 4th, 3x to the 4th minus 2x cubed plus 5x minus 2. Okay. All right. So I skipped x squared, but is that okay? I don't have to have an x squared term, right? So even here, if you look at like what's happening here, that's, so I have x squared, I skipped it, so what that really means is that this would be 0, and then this would be my 5x term, this would be my minus 2 term. So it's okay to have a coefficient that's 0. We don't really put it in there like that. Like I could put plus 0x squared, we just don't. But a sub n cannot equal 0. This first one can't equal 0, because if I said, okay, my largest exponent was the 5th, I had x to the 5th, but it's 0x to the 5th, that term's really 0, so that doesn't really count. But they are, all these coefficients, they are real numbers and they can't equal 0. And n, okay, whatever n is, they have to be positive integers and no negative exponents. So let me ask you this. If I have f of x is equal to the square root of x, what is the exponent on x if I wanted to rewrite it with exponents? 1/2. So x is equal to, that's equal to x to the 1/2 power. It's another way to write it. Does x have an integer exponent? Is this an integer? What are your integers? Whole numbers, like they're counting numbers. So your whole numbers are really 1, 2, 3, 4, like your counting numbers. Your integers also include the negative ones. That's one of the differences there. So that does not have an integer exponent, which means I cannot have x to the 1/2 power in here, even though it's not negative. So no negative, no fractional. It has to be an integer, a counting number. So I also want you to think about what this looks like. This is what the square root function looks like, right? And we'll kind of come back to that. So basically so we don't have to write a whole lot, we just say, no, it's not a polynomial. So that we don't have to write out, not a polynomial. That's kind of the point there that I want to make. Not everything we've looked at is polynomials, and we'll know that for a couple of reasons here in just a second, okay? All right, so some important things about polynomials are shape and continuity first. Polynomials are smooth curves. So far, I feel like that could be the square root function. It's a smooth curve, right? So smooth curve means what it says. It's smooth. There's no pointy anything, so definitely not something like the absolute value function, okay? Has to be smooth. Smooth curves with no breaks. So that means we don't have any discontinuity. I'll be able to start at one end and I can trace the whole thing without picking up my pencil. No breaks, and it is continuous for all real numbers. That means the domain of every single polynomial ever is going to be negative infinity to infinity, right? I can start my pencil at negative infinity, trace the whole thing to infinity, never pick up my pencil. Is the domain of this all real numbers? No, so that's another reason why it kind of doesn't fit into the same category. All right, so degree. The highest exponent n, the highest exponent n is the degree. And notice it says the highest, not the first. If it is written in standard form, like it should be most of the time, then it is the first one. But don't just assume it's the first one that you see. Okay, it's always the highest, but again, in standard form, it should be the first. And polynomials are classified by degree. Any questions at this point? All right, so let's look at these degrees. So all of these functions that are here, they are all written in standard form. So that means that my first exponent is my highest exponent. So let's start from the bottom here. So this first one, the degree is 5. This degree, 4. This degree, because the highest exponent is 3. This one is 2. What is this one? 1. Because we don't put the 1 there. I mean, we can put it there, but like you won't really ever see it, but it's to the first. And what degree is this? 0, because this would be like x to the 0 power, which would still just give you 2. We'll never write it that way, but that's how it falls if we wanted to fill them all in. Okay, so we can classify this first one. This first one is constant. Anytime you just have a number, it's constant. What do we classify the second one as? Linear. What's the next one? Quadratic. The next one? Cubic. What's the 4? Quartic. And the 5th one? Quintic. There are fancy names all the way to infinity, but most people don't know them and they're really not that important, but they exist, just so you know. But if you get to like a 12th degree, you can call it a 12th degree polynomial. You don't have to know the fancy name for it. Okay. All right, we all good? Okay, so end behavior. Do you think end behavior is important? Yes, we've talked about it a lot. Second time today, right? So very important for us. The power and coefficient of the leading term, which is the highest one, not always the first one, determine the end behavior of the function. So we're going to look at this just a little bit differently. Still end behavior. Now, if I have an even power positive coefficient, this is the power function, just f of x equals x squared. It could be anything. So I'm going to give you one that's not a power function. Let's say f of x equals 3x to the 4th plus 2x squared minus 1. Now, if we have a quadratic and we do whatever transformations and we make it like, if this was 3x squared plus 2x minus 1, it's still going to look like a quadratic. We've just moved it around and done stuff to it. But once you get past a quadratic to any other even power, a whole lot of nonsense starts going on in here. This changes up. That middle behavior, right now, you have no clue what that middle behavior looks like. But it's okay because we're talking end behavior. Regardless of what's going on in the middle, since this is an even power positive coefficient, the end behavior is still the same. And that's what we're concerned with right now. So we don't even have to write it all out in words. This is as x approaches infinity, f of x approaches infinity, as x approaches negative infinity, f of x approaches infinity. But as long as we can do this, and we know that that's what the end behavior looks like, that's good for us right now. That's going to be very important in what we do tomorrow. Okay, so that's the end behavior when you have an even power positive coefficient, regardless of what the rest of it looks like. Okay. If I have an even power negative coefficient, like f of x equals negative 3x to the 6th plus 4x to the 4th. Right now, you have no idea what's going on in the middle, and that's okay. We'll get there. But you should know what the ends are going to look like. Because it's even and it's negative, it's going to be down, down. Even is always the same. It's either up, up, or down, down. Okay. Odd-powered positive coefficient, like f of x equals 4x to the 5th. Thank you. Okay, grab one of each of those. 4x to the 5th minus 6x squared. Once again, you have no idea what's going on in the middle there yet, but because it's odd and it's positive, it models the end behavior of a cubic, and your end behavior is down, up. Odd power negative coefficient could have f of x equals negative 2x to the 7th plus 3x squared. Right? You have no idea about the middle behavior, but you should know the end behavior because it got reflected, and it's up, down. So odd is always opposite. Even is always the same. Any questions at all? All right, let's see how, oh wait, I had two more examples I want to do with you. So let's say I have this. So I wouldn't expect you right now to have any clue what that equation is. But because of its end behavior, you should be able to tell me if it has an even or odd power and if the coefficient is positive or negative. So is the coefficient positive or negative? Positive. Is the degree even or odd? Even. Is it an even function? No, because it doesn't have that symmetry, but we have an even power, right? Okay. What if we had this? Even or odd? Odd. Positive or negative? Negative. Okay, makes sense? Those two things are very important for getting to the next steps of what we're doing. All right, so let's look here. It says, using the leading term, give the end behavior of each polynomial. Okay, so I look here, my leading term, my highest exponent is 4. So first of all, what would I classify this as? What's it called? Quartic. Good. And then what does the end behavior look like? Down, down. It's even and it's negative. It's down, down. Okay. We also need to be capable of doing it in words, but sometimes that's all we need because that's kind of what we're going to need for the next part. All right, so then my leading coefficient here, or my leading term here is negative 2x to the 5th. So what do I call this thing? Quintic. Good. And then what do you think the end behavior is going to look like? Up, down. All right, you do 3 and 4. Okay. Frida, what would you call number 3? Quadratic. Okay. Thank you. Quadratic. And then, Avril, what would you call, or I'm sorry, what would the end behavior be? Up, up. Y'all agree with that? Yep. Thank you very much. All right. The next one. On. What do you think you would call this one? In your prefixes? You learned that in chemistry? Yeah? Okay. So septic, y'all agree with that? Does that make sense? Yes. You just use your prefixes. Very good. But there's a different one also. Okay, there's nothing wrong with this one. But when you're classifying polygons, you don't call a 7-sided figure a septagon, even though you could. The more common name is a heptagon. So another name that you could use here is heptic. You would probably be more inclined to use septic, and that's totally fine. I'm not going to have to classify all these. I just want to talk about it. Using your prefixes are good. They do cross over. All right, Layla, what would the end behavior look like here? Pick one. What is it? Down, up. Okay. Good job. Okay. We agree with those? Easy enough? Okay. Good job. All right. We're going to skip 5 and 6. Let's go down to 7 and 8. So this says describe both the power and the coefficient of the leading term. So can't get the equation out of this yet because we don't know how to do that yet. But you could tell me on number 7, is it the leading term going to be in even or odd power? Odd. So this is going to have an odd power, positive or negative coefficient? Negative. Good. This is a negative coefficient. Because if it's odd, it models the cubic, and it's opposite of the cubic. Right? All right, so number 8. Vincent, would this be even or odd? Even. Y'all agree with that? Okay, even. And Prableen, would this be positive or negative? Positive. Good. Okay. Any questions on those? All right. So let's talk about our turning points. So it says the points at which a polynomial function switches direction are turning points. What's another? We've already talked about these. What do we call them? Critical points. Okay. And there's another classification of critical points. Okay, points of inflection are these points of inflection? A point of inflection is where we wiggle, not where we switch direction, but a point of inflection is a critical point. Maximums and minimums, right? And those have another classification, which we'll talk about in just a minute. So we have talked about them. They're maximums and minimums, right? So it says if the turning point is higher than any nearby point, then it is called a relative maximum. We also have absolute maximums. We aren't necessarily going to know on some of what we do if we have absolute maximums or minimums. We'll explain why in just a minute. But remember, even absolute maximums and minimums are relative because it's still about what they're right around. And then if it's lower than any nearby point, we have a relative minimum. Okay. So we have critical points, and critical points include the points of inflection. What's the category that just includes the maximums and minimums? Do you remember? It's what? Extrema. Good. They are extreme values, so it is extrema. And then turning points define where the function is increasing or decreasing. So the last section says using the calculator to find turning points. Okay, we're not doing this, and here's why we're not doing this. Here's why we don't have calculators in our hands all the time to graph these things. Sure, you can push some buttons. You got a graph in front of you on the calculator. That doesn't mean you know anything about it. It means you know how to push buttons on a calculator. The reason that there's a calculator with this is because you cannot find the maximums and minimums algebraically without calculus, and you're not in calculus. Okay, so when we do these polynomials and we find stuff about them, we're not going to be able to find exactly where the maximums and minimums are. Sure, you could push buttons and go, oh, look, the maximum is at -2, 3. That doesn't tell you anything. Okay, it's more important that we're doing the other things. So I left this on here so we could have this conversation, and it'll make a little bit more sense once we start to actually sketch these. We're going to have to estimate where that is, but we'll know a whole lot of other stuff. And we don't always necessarily need to know where the maximums and minimums are. Okay? What questions do you have? We good? All right. Get them folded and taped and get started on your Delta math.